Okay, so in this lecture, what we're going to do is start off by defining what is strain energy. So we want to define this term, and we're going to start fairly logically by breaking it up. So we've got the term strain energy. We're going to first think about strain, and that should be fairly straightforward. And then we're going to explore the energy side of the term and see what's that bringing to the table. So first of all, let's have a little think about strain. Strain is simply a ratio, and it's a ratio that's telling us something about the deformation of our structure. Okay. So when we think about strain, the classic way we introduce this or we think about it is by thinking about a bar, some sort of a structural element, a prop or a tie. And we think about that being subject to an axial load of some description, either a tension or a compression load. So the classic case is a steel bar in compression, let's say. Okay, so let's think about this structural element, and it's subject to compression forces on each end. So let's just sketch those on. Let's say we have some force F here. We've a reaction force on the far side of F. So this bar is in compression. It starts off with an original length, which we're going to call L. Okay, and under the action of the compression force F, it gets shorter. Okay, now it's going to be a very imperceptible change in length, but it will nevertheless change in length and get shorter, and we'll call that new length L1. So L1 is equal to the original length minus the change in length, delta L. Okay, so very simply, put simply, we can say that the strain, which is traditionally given the Greek letter epsilon, is equal to the change in length over the original length. Okay, so it's a very simple idea. Simply take our change in length and divide it by the original length, and that is the strain. So that's the first half of strain energy explained. Now we're going to focus on the energy part. So the way this is going to go over the next 5 to 10 minutes or so is I'm going to introduce some terms. I'm going to provide definitions for those terms, and it's going to appear a little bit meandering, and you might at some stages over the next 5 or 10 minutes start thinking to yourself, why is he explaining this? And where is he going with all this? But trust me, when we get to the end, before we wrap up this video, I'm going to bring it all back together and it should make more sense. So just stick with me while I define a couple of necessary terms to help facilitate our explanation here. So we're kicking off here with energy. So what is energy? Well, one way to describe energy or to think about energy is required to do work. Okay, so I've tried to explain one term, but then I've kind of introduced another term here which needs a definition all of its own, work. So energy is required to do work. Okay, so we're going to come back, we're going to circle back and think about a definition for work in just a minute. But before we do, we want to further elaborate, if you like, on energy and think about the different types of energy that we might have. We have kinetic energy and we have potential energy. They're the two categories of energy that we're going to be thinking about. So kinetic energy is the energy a mass has due to its motion. Okay, so you might remember from your physics classes that the kinetic energy of a mass, which we will call here U subscript K, that's going to equal, for a mass that's traveling at some velocity v, the kinetic energy that it has is a half mv squared. So we're kind of just explaining this here for completeness, but what we really want to focus on for the purposes of our discussion is potential energy. That's the one that we're going to elaborate on further. So potential energy is energy that is stored in an object, or energy that an object has due to its position, or more importantly for us, its state of internal stress. Okay, so stored energy due to an object's position or, in particular, state of internal stress. Okay, so we've talked about energy. It's required to do this thing called work, which we haven't talked much about yet. But energy itself is broken down into kinetic energy, which is energy an object has due to its motion, or potential energy, which is energy that an object has due to its position or its state of internal stress. So now let's circle back here and think a little bit about work. Okay, what is work? Again, back to the early physics days here. Work is simply the let me see, what's the way to put this? Well, let's think about it this way. a force does work when it moves through a distance. Or put another way, work is done by a force when the force moves through some distance. Okay, so if I have a mass and I apply a force to that mass and the mass moves, well then the force that was applied to the mass is also moving. And in moving that force through the distance that the mass moved, work was done. So I've probably confused you more than helped you with that particular explanation. So let's get some notes down on the page here, right? So what is work? Work is done by a force when the force moves through a distance. That's the simplest definition here. Okay, so let's think about a basic scenario here. We've got some frictionless plane. We have, let's say, some mass m that's sitting on that plane. We apply a force F to the mass, and that's going to cause our mass to move through some distance, which we'll just call delta. Okay, so F is going to move through the same distance, delta. So what we're saying here is that by moving the mass m through the distance delta along the line of action of the force, so delta must be in the same direction as the force, that's important. The force F does work on the mass. So let's wrap that up in a couple of notes here. So by moving the mass m through a distance delta, where delta must be along the line of action of the force, we can say that F does work on m. Okay, so wrap it up in an equation. Work is equal to F times delta. Okay, and the units of work are Newton meters, which makes sense because newtons is the units of force, and delta has units of distance, which in this case will be meters. So it's Newton meters, or we could also say joules. Okay, so that is work. Now what we're going to talk about is the principle of conservation of energy, and we're going to talk about it pretty briefly here. So again, stick with me. I know it sounds or it looks as if we're jumping all over the place defining terms here, there, and everywhere, but it will make sense in just a couple of minutes. So let's define the principle of conservation of energy. So what this principle says is that energy cannot be created or destroyed, only changed from one form to another. Okay, and how a good way of conceptualizing this or thinking about this is a simple case of a ball that's sitting or standing up on top of a hill. So let's imagine some sort of an incline hill here, where we go from a high position to a low position, and we have some ball that's on the top of the hill here, and let's say it's stationary at this point, it's not moving, stationary. Okay, so if that ball's at the top of the hill, we could say that its potential energy is at a maximum and its kinetic energy is zero, because remember, it has no velocity, it's stationary, and so the kinetic energy must be zero. So we would summarize this situation or this state by saying potential energy is at a maximum. It's at a maximum because it's at the top of this hill. And remember, we said potential energy was energy that an object has due to its position or state of internal stress. So in this case, it's due to the position of the ball. Now we said the kinetic energy was zero because the velocity is zero. So now we think what happens, let's say someone comes along and pushes this ball down the hill. The ball is being pushed and it's sort of flying down the hill here, and then at some point it gets to the bottom of the hill. It's carrying its maximum velocity, but it's at the base of the hill. Okay, so its height, if you like, is zero rather than being at a max in the left-hand diagram. So in this case, because the height is now essentially zero, it's being reduced from its maximum down to its minimum height, we can say that the potential energy is zero. But because it's at the base of the hill now, and it's traveling as fast as it's going to travel, the kinetic energy is a maximum. Okay, so the key thing here, we've kind of labored the point a little bit, but the key thing here is the overall state or energy state for the ball has not changed. So the total energy remains unchanged. All we've done is transferred the energy from one form to another. And that essentially is the principle of conservation of energy. We can't create or destroy energy. All we're doing is changing it from one form to another. So the total energy remains unchanged. So let's now think about this other sort of phrase that we dropped in up here, which said that potential energy was stored energy due to a state of internal stress. Okay, so this is where we're starting to bring everything together. We're going to start bringing the whole thing together. So let's think about, now we want to develop this idea of stored energy. So our spring has an original length of L. So that's our original length. And surprise, surprise, we have a force that comes on and is applied to the spring, and we'll call that force P. So we all know what happens when we apply a force like that to a spring. The spring is going to compress and get shorter. So we can see that there is a change in length in the spring, which is delta L. Okay, so now after our preceding discussion, we can see that that force P has moved to the left through a distance delta L. So P has done work on the spring. So that work W is equal to P times delta L. Okay, and again, let's just remind ourselves that has units of Newton meters or joules. So now that spring has now been compressed and it's trying to expand. So we've got stored energy in the spring. Okay, so this is where the whole thing comes together. P has done work on the spring, but corresponding with that, are happening at the same time as that, there is energy being stored up in the spring due to the change in the state of internal stress within the spring. So let's just summarize that. So we now have energy stored in the spring. All right, so in work energy terms, which is what we started out with, we would say that there's work done by P on the spring has been transferred into stored potential energy in the spring. Okay, so now we're bringing back all of these terms that we were defining previously. So let's state that again. P has done work on the spring because it has moved through a distance delta L, so force times distance equals work. So that's the work done by P on the spring, and that's being transferred because remember the principle of conservation of energy. We can't create or destroy energy. We've got to change from one form to another. So the work done by P has been conserved or transferred into stored potential energy within the spring. That's the key message we're trying to get across here. So in work energy terms, Okay, so that's the key message here. Work done by P on the spring has been transferred into stored potential energy in the spring. Okay, so it's all very well talking about springs. They're a nice entry point or entryway into the discussion of stored energy, but how does that relate to our steel bar or our structural member? So now we're going to circle back and think about how all of this relates to our structural element. All right, so let's draw the equivalent structure. So we have a force P comes onto our structural element, and that will generate a reaction back here of P. So our pin support doesn't go anywhere, but our structure does get shorter. In exactly the same way the spring got shorter, our structure, our bar, will also compress. Okay, so it's essentially the exact same behavior. So P does work on the bar because the bar gets shorter. So the work done is equal to, again, P times delta L. I've not drawn delta L on here, but that's the shortening of the bar. But instead of it being a spring, the bar is linearly elastic. Okay, so it's still behaving like a spring. It's because it's linearly elastic. It's trying to expand again. It's trying to recover its original shape. So it's behaving, although it doesn't look like a spring, it's behaving exactly like a spring, trying to return to its original shape, to its original length. And so it too has stored energy, and we call that stored energy in the context of a solid structural member like this, we call it strain energy, and that is the key. That's the closing of the loop here. To get down a couple of notes on this, we would say the bar is linearly elastic, and that means that it's trying to return to its original length, just like the spring. And in the same way the spring had stored energy, the bar has stored energy, and we call that stored energy strain energy. All right, so let's again throw that into work energy terms. So we would say work done by P on the bar is conserved as an increase in strain energy in the bar, just like our spring. So the behavior of our spring, which I'm shown here as a sort of a classic shock absorber, the behavior of that spring is mapping perfectly onto the behavior of our structural elements. So we introduced the idea of stored energy using the spring, because everybody's familiar with the behavior of a spring. When you squeeze it, it compresses and it tries to push against you, and that pushing against you is that internal stored energy. But actually, that behavior is mapping perfectly onto our structural element. Our structural member is behaving the exact same way. If we compress it, it's trying to expand and recover its original length, and that is essentially the manifestation of the internal strain energy within the structure. The same would be true if we took that bar and we tried to pull it apart, we tried to extend it. It would try and squeeze or shorten back to its original length. And again, that's just the internal strain energy, which is a conservation of the work done by the force that was causing the change in length in the very first place. So that is the basic concept of strain energy, and it is on that basic concept that the whole analysis procedure of virtual work develops and builds from. So we'll see how that works over the remainder of the course.